All
Okay,
right.
so
I
we're
heard the little
recording.
voice. Excellent. Okay, then yeah, we can get started. So my name is Lauren. I work at GE Vernova. So I think this class has already done one design challenge. Today we will be doing another on heat exchanger design. So I'll go through a little bit about GE Vernova first and a little bit about me. And then we'll get into a little bit of information about power plant design, and then I will introduce our design problem. I don't think I'll talk for a full hour. I might, but if not, especially for anyone that is online, feel free to drop questions in the chat if you have any questions that come up, or unmute if you feel comfortable doing so, and then we can tackle any open questions at the end with any remaining time we have. So, about GE. So, GE Vernova is the energy arm of what used to be one big business, GE, General Electric, which has been around for over 100 years, started by Thomas Edison. So, the GE Vernova business is our energy business. So, you can see here on the right hand side of the screen that we have a few different arms. So, power generation, this can be gas power, hydroelectric, steam. We have wind energy, as well as electrification, which can be grid technology, and then accelerators. Generally, we have a research and development arm. So you can see a lot of things on the slide here, but we are a very big company, very influential in the energy industry. So 25% of the world's electricity is generated by our equipment. Um, a lot of other numbers on the slide, but all to say we generate a lot of power using a lot of different technologies, and we are all over the world. I personally am based in Greenville, South Carolina, which is where one of our larger gas turbine manufacturing plants is. But we have offices throughout the United States and throughout the globe. And a little bit about me, just so you know who's talking to you. I am a proud Gator. I graduated in 2020, as you can tell by the photo, in the midst of COVID. So I am familiar with the asynchronous environment because of that. And from there, I joined GE. Um, and while at GE, I got my master's in mechanical engineering as well at Georgia Tech. At GE, I have done the rotational program before I went full time as a plant performance engineer, and today I work as a direct air capture engineer. So, if you have any questions for me about just early career engineering experience, I am more than happy to talk about that. I do support recruiting at UF in the fall, so there is a chance that you have met me on campus or that you will if you are interested in GE. So, power plants. Today, as I said, GE Vernova covers a lot of power technologies, but today we will be talking about combined cycle power plants. This combined cycle, as the name implies, combines a combustion gas turbine for power generation with a steam turbine for what we call the topping cycle and the bottoming cycle. So you have a gas turbine, which uses natural gas as a fuel for combustion that creates rotational energy that is turned into electrical energy through a generator. And the exhaust from that gas turbine is still very, very hot. So we use the residual temperature in that exhaust to boil water in what's called a heat recovery steam generator. You can see that here in the middle of the screen if you see my mouse. So we boil water, and that water is sent through a steam turbine to squeeze out even more energy. So then that inertial energy is turned into electrical energy with a second generator. So two different arms of a combined cycle power plant. Today, as we talk about heat exchangers, we will be more focused on the bottoming cycle. But for your information, this is how the whole system comes together. This is a general process flow diagram that you can see, and then on the next slide, I'll show you what the hardware actually looks like. So, as I said before, we looked at a gas turbine as a trapezoid that shows more what it looks like in real life in a very shiny, pretty view. So as I said, we start with our gas turbine, which is number one here in the middle. This is where combustion happens. So this big rectangular box draws in air, and there is natural gas that's injected, and combustion happens in expansion. So then your exhaust goes through this big block. this is where the boiler exists, as I said. So we call this the heat recovery steam generator. This is where it is a very giant heat exchanger. So there are tons of coils of water that is boiled and pressurized. And that boiled water comes all the way over to our steam generator, steam turbine over here, where it is expanded to generate more power and then goes to our condenser. So the circuit between the steam generator and the HRSG is a closed circuit. So we need to be able to go from boiled water, vapor, right, back into liquid water. So that's the importance of the condenser. And the condenser is what we will be heavily talking about today. Another view, so we just looked at the main equipment circuit for GE, but I just wanted to give an idea of scale as we're stepping up our understanding of how big these power plants are. If you saw this previous picture, you probably thought to yourself, if you've seen a power plant, that this looks a lot smaller and a lot cleaner than a whole power plant. There's a lot of supplementary equipment that goes into bringing it all together. So as we saw before, you can kind of put together the same picture of air comes in through these giant filters, gas turbine, and then our boiler or HRSG, and then stack. This is actually where your exhaust gas goes out the top. And in this case, the previous view, we saw everything on one line, and this configuration, the steam turbine, is actually over here to our left. So these two skids actually share one big steam turbine unit that's in this box. The clue you can find is these are the bus lines for the generator, so it's easy to find the steam turbines, to find the turbines because they're attached to generators, which are attached to the power equipment. So we can say, okay, here's some power equipment, there's one turbine. Here's some more, there's another gas turbine. And then where's the steam turbine? Probably attached here. And finally, what we hadn't touched is a lot of power plants you'll see have cooling towers. So in the back here, you can see an example of a wet cooling tower. There's other auxiliary equipment such as water treatment that you might see on different plants, and of course, power transmission. We will not get into all of that today, but just a high level view of what a power plant may look like. So as I said, that is the overall combined cycle. Today, we are thinking about heat exchangers. So we will be focused on the condensers that are downstream of the steam turbine. So as I said, the goal is to take that steam and condense it back into water so you can continue that loop. There are a few different ways that you can provide that cooling duty. One of them is using air. So as is implied, you're blowing air over steam in order to condense it. That does require a high volume of air and fans. A secondary way that we will walk through is water-cooled condensers. This uses a closed circuit of water to cool the steam and condense it. And finally, there are once-through condensers. We won't go through this in detail, but the idea of a once-through condenser is it can use a available body of water, and as the name implies, pass through once that body of water, such as a river, a lake, an ocean, and reject some of that heat from the steam to the body of water. This is much less popular, especially nowadays, because of the potential environmental risks. So for the sake of these discussions, you can be aware that those exist, but we will be focused on the air-cooled condensers and the water-cooled condensers. So as I said, starting with the air-cooled condensers, they are indirect heat exchangers that use airflow, ambient air, to cool down the steam and condense it. So you can see a couple different visualizations here of steam will come into these big header pipes, pass through these fins. You can see detailed views of the fins here, and then condense. So you can see the volume comes in very large, comes out very small as it condenses. And air is drawn through fans, sucked over these fin tubes to cool down the steam that comes in until it condenses into a water vapor before it is returned to go back to the power circuit. Water-cooled condensers are a very similar philosophy, but instead of cooling with air, we're cooling with water. So I have an example here on the right. So you start, once again, we start following our steam path, high volume is coming through. Now it's passing over tubes of liquid water that is cold, um, and the steam condenses until it pools at the bottom as condensate and comes out the bottom. Typically, as I note here, a lot of condenser designs are water boxes. They don't have to be, but what that means is you can see, even though there's individual tubes passing through here, they all have a shared header and a shared exit. So you have a large water volume at the front. All that water is pushed through the tubes, goes all the way around. So passing through the steam heat exchange area twice before it comes back out the outlet. If you have a water cooling tower, you now have a large volume of water that has picked up a lot of heat. So you need to reject that heat somehow before you can use it again for the next cooling phase. So with that comes cooling towers like we saw in the very first image. So as we see in this image here, a cooling tower will take the heat that you've just picked up during the condensing process, and then cool it back down. For typically this involves some form of air exchange. So with the view we see here, you take water and you rain it down as you draw air over it. That is a different methodology for air cooling. So you can tell with this example of this wet cooling tower, this is direct cooling versus the air-cooled condenser example we saw before is indirect cooling with the fins. So with this method, the water does rain down back to the bottom and it is a closed circuit, but you will have some amount of water loss that does need to be made up over time. So that is a consideration for these applications. So this is more for your information. Today we will be focused on the condenser itself, but depending on whether a water condenser is used versus an air condenser is used will drive whether you need a cooling tower. So when you consider designing a power plant and what kind of condenser you're going to use, there are a few different things to take into account. So first of all, what kind of heat exchanger are you going to be using? What is your cooling source? So as we just discussed, you can either only use air or you can use water, and typically that is paired with air. So there's typically an air element involved. Um, the condenser itself, the inlet condition is typically saturated steam. You want the temperature at the outlet of the steam turbine to be as low temperature and pressure as possible because that indicates that you've extracted the most energy. If your pressure is higher, if your temperature is higher, that means that there's less energy that has been extracted and is still remaining in your gas stream. So for the sake of the discussions today, we will assume that the inlet conditions for the condenser is saturated.
Laura,
And finally, go
sorry to
ahead.
interrupt you. There's a question in the chat which I can
Yeah.
read for the benefit of the recording, which is so even if you are cooling with water, you are still going to have an air cooler to cool the water you heated up?
Yes, most likely. So as I said, if you have a closed cooling water circuit, you've picked up heat energy that you need to reject somehow. Typically, as I said, that is through a wet cooling tower, which involves an air element. You can have another water-to-water heat exchanger instead if you do once through cooling. Um, so very similar to the once through condensers I mentioned at the beginning. But as I said, once through cooling, whether that's for cooling towers or condensers, is not popular these days due to the potential impacts of uh, why is that word leaving me? Like water climates. So
And sorry, and by that you mean you're essentially heating up what would otherwise be like a natural water supply, like a river or
correct.
lake, which then causes, well, you know more than I do, but I'm guessing unwanted animals and unwanted growth of algae and so forth.
Exactly. So the risk is you're increasing the body of water by, let's say, locally half a degree. You can control it to be very small, but there are typically some implications of that small temperature rise. The other concern is you're drawing water into a mechanical system, right? So even if you have filters, you have gates, there's always the risk of sucking up a fish or having animals that are just stuck against the gates. Um, So from that perspective, there are designs that can minimize those risks, but generally it is less ideal. So I think if you're feeling creative and want to consider that for this project, you're more than welcome to. But for everyone's information, it is a less standard design, especially for natural gas combined cycle plants. Okay, hopefully that's clear. I don't see typing, so I'll take it as a yes. Yeah, so I think this slide tries to lay that out as well, that you either are working only with water to air directly, in which case you don't need a cooling tower at all, or you're doing water to water and then a secondary heat exchanger, which is water to air. So your final temperature is going to be dependent on the approach temperature that you can achieve with the heat exchanger you select. So for an air-cooled condenser, it's just what approach temperature can you achieve with the condenser. And if you have the water-cooled condenser, now you have to consider both the possible approach temperature of the condenser design as well as the cooling tower. Right. So with that, the design problem. So hopefully everyone has been to Gainesville, Florida, even if they're not there right now, and has walked through Depot Park and noticed that there is a power plant hiding in downtown Gainesville. So I stole this view from Google Maps. But like I said, you can see the power plant from Depot Park. I used to live near there, walk along the street, see the cooling towers. So this is a much smaller footprint. You can see here 110 megawatt combined cycle plant. For reference, the images I was showing before are closer to like 500 megawatts. So they have a small gas turbine as well as a steam turbine to generate power for the Gainesville area. So I think with the clues that I gave you before, right, we can see we have this big air intake here that's being pulled, and you have a set stack. And then you can see a lot of piping. I would assume that this is where the boiler is located, as well as a secondary stack. And then you can see some power equipment here. So my guess would be that you have a turbine hall here, which is where the generator is located. I also grabbed a picture of the cooling tower. It was hard to fit all in one screenshot. So this is co-located nearby, but did not fit into this picture. So they recently replaced their steam turbine. So the question for your groups today will be, can you design a new condenser for this GRU plant? And I included a little link here. Of course, you can Google away and find a lot of information about this plant, but I thought this was a good starting point to get some information about the power plant itself. As a public utility, there's typically a lot of information online. I think this tells you the general megawatt rating of the gas turbine, steam turbine, and it tells you the operating hours and things like that. So we went over it a little bit, but we'll talk a little bit more about things you have to consider when designing a condenser. First of all, is footprint. So you likely have the awareness that if you're using air, you need a lot more flow than if you're using water for cooling. Water is much more effective at cooling. So when we're thinking about a heat exchanger between the two of those, if you prefer air, do you have the space for that? Second, as implied with what I just said, you have to choose your cooling fluid. Is there any limitations on the availability of fans or of sourcing water to create the cooling fluid that you need? Third is the heat exchanger design that you want to consider. I think you just went through heat exchanger design, so hopefully you have some ideas in your head. Parallel flow, counterflow, water box as the example I gave before. There are a lot of different opportunities for how you design your heat exchanger once you've decided your cooling fluid. Back pressure impacts. So I mentioned this before. You do not have to consider this for this project, but just for your information, we want the pressure and the condenser to be quite low because that means that you have a higher pressure difference across your steam turbine, which means more power out. And finally, auxiliary power. So this is considering depending on the heat exchanger you design, you either need a pump if it's water to circulate the flow that you're using, or you need a fan to draw the air that you're using. That takes some amount of power. We're trying to design a system that produces power. Um, so as you design your heat exchanger, it will likely have some element of pressure drop. And with information on your pressure drop and your flow selections, that will drive power consumption either across a fan or across a pump. So that's something to think about as you're designing the system is how can we be the most efficient of providing the cooling duty that we need while consuming the minimal amount of energy possible. So an overview of what we're looking to see for this project. We'll go from left to right. So starting on the left is an overview of the GRU site. So I will give you some starting information to consider, but I hope to hear from you a little bit more about your business statement, your problem statement of the GRU plant, such as considerations about the fact that you are in hot and humid Florida. How does that change your cooling fluids selections, available water, as I said, site size. I think this is a very interesting project because you are in a downtown area. Typically, power plants are in the middle of nowhere and have a lot of land, but you are a little bit more restricted with this project. Um, and then you'll have to, of course, the number one criteria is can you reject the heat that you're required to reject to condense our steam? Um, with that, as I said, my goal from you is for you to propose a condenser design for me. So I would like to hear what is the reasoning for the final outcome that you propose. So the size of it, what did you consider about the site? What are the cost implications? And more generally, what kind of heat exchanger did you select? When it comes to that, the actual calculations, you will need to evaluate what flow rate is required for the cooling fluid that you've selected, the heat rejection required to condense our steam. And as I said before, footprint, of course, is very important being in a constrained downtown space. Um, and I would like to see some evaluation of CapEx and OpEx. So CapEx is capital expenditure, OpEx is operational expenditure. So CapEx is how much money did you spend up front, whereas OpEx is how much money are you spending due to power consumption. So with this, I think we can keep it simple. With CapEx, I'm looking to see considerations of material cost for the heat exchanger you design. And with OpEx, as I mentioned before, you will require some fan or pump power based on your pressure drop. So I would like to see an evaluation of that. So some information about the problem statement here. What we have given to you is the outlet conditions of the steam turbine. So, and unfortunately, this is an imperial unit. Depending on what projects you work on, often in the US, these units do come in an imperial. So be prepared for unit conversions. So we have 350,000 pounds of steam per hour coming into your condenser at 120 degrees Fahrenheit. As I said before, we should assume saturated conditions and the full focus of your condenser is to condense. We don't need any additional cooling. So you can assume that your inlet and outlet temperature of your condenser is the exact same. And I've given some basic information here. As you know, we're located in Gainesville, Florida. If you need ambient conditions, I have grabbed, I believe these are average summer temperatures that you can use here. And a standard operating hours you can consider if you do any sort of power consumption and power cost calculations. Additionally, if you choose to go with a water-cooled condenser, I have given a standard wet cooling tower approach temperature for you to use because we are only asking you to design the condenser. You don't have to have the additional step of designing the cooling tower. So on the right, I've given you a few strings to pull on what you'll need to determine yourselves. So as I said, this will be a saturated condition at the outlet of the steam turbine, so the inlet of your condenser. So you'll need to find what is the saturation pressure at 120 degrees Fahrenheit. The heat duty that you'll need to reject, you can find the latent heat of water at 120 degrees Fahrenheit. And that plus your mass flow will help you determine your thermal duty. Your approach temperature you will need to assume if you choose to do the LMTD method, and that should be assumed based on the heat exchanger design that you propose. Um, and then remaining considerations, largely you can use the power of Google, whether that's Google Earth for footprint evaluations as well as for power costs. I'm not giving you a firm value, but as I said, utility values are pretty readily available. So I know this is a lot of numbers on a page. So next I give a visualization of the exact same thing. So on the left here, we have our steam turbine. Coming out of our steam turbine, as I said, is your 350,000 pounds per hour of hot steam. You will design your condenser so that on the outlet, it is no longer steam, it is water. Um, and you are responsible for designing this heat exchanger. The inlet conditions you have the power to determine. So I have this question mark here because if you are doing a water-cooled condenser, there will also be a cooling tower upstream. So this is supposed to represent the cooling tower if you choose to consider it. So that's where I gave the approach temperature of the cooling tower if you consider it. So we can say if you choose to draw in air as your temperature. If you're using water, you can assume the approach temperature I've provided. You will have to determine what is the flow rate needed to provide the cooling duty based on this, based on your design. And with that, you will, as well as the mass flow rate, you will provide what is the outlet temperature of your condenser. Last project, we are looking to have a pitch from your team. So we're looking for a 5-minute pitch on what is your recommendation. Tell us about what kind of condenser you've proposed for this problem and what drove your outcome. What is the footprint in the application? Um, considerations for operational power, as I mentioned before, as well as the implication of material costs. As I said before, this can be simple estimating the material mass and material selection, whether that's copper, aluminum, etc. Um, and we will be, and we might just be me, but GE will be providing 2 different time slots for some teams to give these presentations live. So we will have, I think, a total of 10 slots that give 5 minutes to present and 5 minutes for us to ask questions. I don't know how much extra credit, but I believe there will be extra credit if you are brave and present to us. And it will make me very happy to get to hear these presentations live. So please be bold and come present to us. And I will have this. Here's the schedule. So today we're talking now, obviously. On Friday, we will have a brief office hours for any questions that come up. And then on Monday and Tuesday, we will have those 2 time slots if you would like to present live. And then hopefully we will have some exciting closing thoughts and feedback for you based on how your presentations go and what bright ideas you bring to us. So I will have a quick 30-minute recap on the 24th to have some closing thoughts. All right. I guess I blazed through that, but any questions?
Just out of curiosity, why can't you use like a cooling tower in replace of the condenser? Is it just because of like it can't handle like the mass flow rate coming directly out of the steam turbine?
You could. You absolutely could. So the example I gave was, oh, sorry. Let me think about that actually.
It was a water turbine that was then going to the water cooler, right?
Yeah. So the benefit of if you have a closed, so the benefit of using a wet cooling, sorry, water cooled condenser is that you have a closed circuit here. So with a cooling tower, when you're raining down the water, you can intake particulates and contamination, which we don't want to send to the steam turbine. And there's some amount of water that just vaporizes and is lost to the process. So that's less appealing. due to the contaminants due to the water loss. Does that make sense?
Yeah, that makes sense. Thank you.
And I believe the condenser is operating at a small vacuum. So once again, a benefit when it comes to the amount of pressure rise, pressure loss across a steam turbine for power extraction versus if you're open to atmosphere, you're limited to atmospheric pressure. Good question.
Any other questions for Lauren? Well, we've got her here live. And you're welcome to type in the chat and I'll read them if you want to stay anonymous.
Hopefully the problem statement makes sense.
Yeah. So I guess maybe just to clarify. So if you go forward maybe like 5 slides to the requirement. Oh, hang on, there's a
Yeah,
question, but we'll do that in a second. Keep going, keep going, keep going, keep going, keep going. Okay, more than 5 slides, sorry. Yeah, right there. Oh, back one.
this one.
Yeah. Okay, so condenser inlet, if water ambient plus 7 Rankine. So that's
Rankin.
yeah, that's let's see, I gotta think about this condenser inlet. Okay, so in other words, if you're going with a water to water, um, your temperature is hotter by 7 degrees Rankine than if you're using air, and that's because the water that comes out of the cooling tower is higher than ambient temperature.
Right.
Okay,
Yeah, because if you had a infinitely large cooling tower, your water outlet temperature could be the same as the air temperature, but that is not necessarily economical. So 7 degrees is a pretty typical value that we see for the temperature difference. So that's a trade-off that students can consider is the benefit of water being more effective for heat exchange, but you have to start with a higher temperature
it starts
than for
hotter.
air.
Yeah. Okay.
Yeah.
Okay. Interesting. All right. Here, let me read for the benefit of the recording. Okay. So, question: is the goal to reject as much heat as possible? If not, what else should be considered?
Right. So the goal, there is an explicit amount of heat that needs to be rejected to condense the volume of steam. So there's a latent heat of vaporization that you can look up. It's typically, I think, in steam or water tables. If it's not in your textbook, it's easily Googleable. So that is typically a function of temperature and pressure, or maybe just temperature. Um, so based on that latent heat as well as your flow rate, you'll be able to determine the energy that you need to reject. But that will be a fixed number.
Should we apply like a safety factor to that number, or should we just do it like explicitly?
That's a good question. I would do it explicitly because as for I think the simplicity of the prompt, I'm just asking you to condense the water. And if you go beyond that, you are applying some amount of subcool to the outlet. So I think just for consistency of calculations across all teams, you don't need to apply a safety factor. But I think in real life, we would have some sort of subcool at the outlet so that we ensure full condensing in all operating conditions.
Okay, that's good to know. Thank you.
So, follow-on question in the chat. So the goal is to minimize costs while rejecting the specified amount of heat.
Yeah, cost and power. So can you design a heat exchanger that generally fits where we're trying to put it? that is relatively cheap and doesn't consume a lot of power. So I don't have a firm definition that you have to apply to compare your capital costs versus your operational costs. But for example, if you calculate your power consumption, I have given you operating hours per year, so you can use that to calculate an equivalent operational cost. So you can evaluate systems that maybe consume a lot more power and are cheaper versus a system that is more expensive upfront, but more energy efficient.
So to put a dollar figure on it, would they be using like the utility electrical rate?
Yeah.
Like
Hmm.
I have no idea what it is in Gainesville, but in my mind, it's like 6 cents a kilowatt hour, something like that.
Yeah, something that's the unit at least is like
Yeah,
dollars or cents per kilowatt.
kilowatt, not kilowatt hour.
Kilowatt hour.
Yeah, kilowatt hour.
Kilowatt hour.
Energy, not value.
Sorry.
Yeah, yeah.
Yes. Versus what I expect to see when it comes to the capex is, let's say copper costs $10 a pound, and you have some estimation of what the size of your heat exchanger is. You can give to me estimation on at least the material cost to produce this heat exchanger.
Okay, but no manufacturing costs.
If you're feeling ambitious, I think you can look up, like, we call them like EPC factors. Generally, there are some conversions you can do for quick assumptions on what your material cost is and how it might scale to as built cost. Um, so I would be very happy if someone presented on it, but for it being a week-long project.
Yeah, yeah, I got you. And well, and to be able to make like an apples to apples comparison, right? Between
Yeah,
um yeah, it's I guess the underlying assumption is the materials are more expensive and the cost to turn those raw materials into whatever heat exchanger you're imagining like scales linearly with the cost of the materials.
yeah,
So if you minimize the cost of materials, you've also minimized the labor to manufacture.
right.
Yeah. Other questions while we're here and we have Lauren live? Yeah. So I've got one that actually came up. So you said the magic 4 letter word, which is LMTD.
Yeah.
Um, so we just and I'm maybe jumping the gun here just a little bit because I gave them the LMTD lecture in the middle of the week last week.
Mm,
And then I followed up with the effectiveness NTU, which dropped like basically yesterday. So they probably know all about LMTD by now, but maybe not effectiveness NTU. You mentioned LMTD, but could they apply effectiveness NTU to this? Like, would they even want to? I guess. And the reason that I ask is because this is that special case where you have like one of the streams is constant temperature, right?
yeah.
And so it's actually like there's a effectiveness NTU expression specifically for this case. And so I wonder if there might be some benefit to using that approach.
So now you're testing how rusty I am on
Yeah,
heat
sorry, I
again.
don't mean to put you
But
on the spot, but
so LMTD, you need to know the inlet and outlet conditions for both sides.
yeah.
For effectiveness, I would have to Google unless you know handily what inputs you need in order to determine to apply that method.
So you need to know less information. So you just need
Mm.
just the inlet conditions and the mass flow rate and the identity of the identity of the working fluids. So that you
And
can,
then you would assume some effectiveness based on the heat exchanger selected.
yeah. So the two are
Mm.
related. So I think you could
Yeah.
actually, so you could basically you could do like effectiveness NTU in reverse, right? In other words,
Mm.
um, you know I got to think through this. You know the amount of heat that you need to reject, right? That's a value that is
Hmm.
basically set by. I don't want to give away too much, but that's set by the parameters that you've been given.
Yep.
So in the effectiveness equation, you can find Q. And then
Yeah.
I think I'm right that you can also find Q max, right? Because Q max is based on the difference between the maximum temperature extremes that um, the heat exchanger experiences. Um,
Yep.
and so with that, you could find, well, no, okay, yeah, you can find effectiveness. You can, yeah, that gives you effectiveness. And then you could use an effectiveness NTU for a constant temperature um, uh, condensation, right? That's the water side.
Hmm.
And that would give you an NTU.
Yep.
And the thing that you don't know is U times A, right? So that would actually give you the appropriate. You could get as far as UA using that,
Yep.
right? And then that's
Hmm.
that's that's where the kind of open-endedness comes in. Or you get the
Right.
same spot with LMTD, but I'm thinking like it might even be easier to do it that way. And so then the challenge
Yeah.
becomes how do you pick UA, right? So,
Hmm.
so you need an appropriate A, and then you need an appropriately high U, which is a combination of H's basically,
Yep.
to hit that NTU. So I think
Hmm.
you could actually do it that way.
Yeah. Yeah, I'm looking at the equations on the side as you're talking, and I agree. I think either is manageable.
Yeah, either approach will work. So, which is actually very, very cool. I gave them I'm very proud of this. I gave them an example in the LMTD lecture, and then
Yeah.
I solved the exact same problem in the effectiveness
Mm.
NTU lecture, and you get within like 0.1% of the same value. But it's very unusual to find a problem that you can work in both directions. So this I think just happens to be one of those problems, just because of the way that you set it up. So
Wow.
which
Go
is
me.
good, right? Because now they can do it either way, right?
Yeah.
So the LMTD comfortable people can use that, and the effectiveness MTU comfort people can do that.
Right. Right. And I think you dropped a good clue there too on the consideration of UA, of the area of the heat exchanger is going to drive your footprint. Or if you choose a more conductive material, for example, that maybe that's going to affect your costs. So those are the kind of considerations you need to get to once you've solved the fundamental equations.
Yeah, yeah. So they'll have to go through and like think through all the different. Well, and then I actually did this on purpose. So in the effectiveness NTU, we solved for sandbag. We hadn't done heat exchangers by that point. So
Mm,
they did basically enhanced fin design for the Sandvik project, which was an oil cooler on one of their mining rigs. But there's a special section in the book which is not normally covered in the undergrad heat transfer class, but it's in the book, on compact heat exchangers. And there's
mm,
a section in there on how to find pressure loss, which
okay.
which in theory, since they've all taken fluids, which is a prerequisite, they should be able to do it from fluids. But there's
Hmm.
actually it's a special specific section in the book on how to do it for compact heat exchangers. So that, I think, to me is the big, the $64,000 question is, you can design UA all day, but then in the end, when you calculate the pressure loss, it's how much pumping power do you need? And this thing has got to be really compact, right? Because it's got to sit like, basically on a urban like plot of land right in the middle of the city.
Hmm.
So they're probably going to end up with some sort of compact heat exchanger, I would imagine, at least some configuration, and then they're going to get like massive pressure drop, and then they're going to realize that the pressure drop is so big that it negates all of their like design work, and they're going to have to go back to the drawing board and come up with something that's a little bit less lossy. So that's in
Right.
my head, at least, that's what I'm imagining kind of the iterative process is going to be. They're going to design something that looks great on paper, and then they're going to look at the pressure loss and be like, nope, and then they're going to have to go back and like make channels bigger, make like fins less like finny, like to get the pressure loss under control. I mean, I
Mhm.
think I'm right, and I didn't actually do this calculation. I probably should have before I said this, but I think I'm right that you can actually like over pressurize a heat exchanger to the point where you could damage it, right? I don't know if you ever encounter that, but that's in like really small compact heat exchangers, that's a big problem. You can over
Mm.
pressurize them and they'll actually start leaking because you break through the thin wall with like
Oh, yeah.
overpressurized fluid. I don't know if that happens in large scale like power generation, but it definitely happens at smaller scale.
I mean, I definitely have to keep a we what we do is we'll apply velocity limits and say, okay, what is a reasonable velocity limit? And that's typically closely tied to the pressure drop that it induces, right? So if I have a very coily heat exchanger, if my velocity is too high, the pressure drop is going to be too high, which drives up the system pressure, which can lead to leaks.
Yeah,
So that is something we have to consider.
yeah. Did we didn't actually give them a like a maximum velocity or maximum pressure, did we?
No,
No.
no. I think for me, the interest of this is to see the judgment and what
Yeah,
is the reasoning.
okay. So they could conceivably like the glitch in the matrix is they could potentially choose a really, really lossy compact heat exchanger for their UA, and
Mhm.
provided the pressure loss isn't so high that it breaks the bank on pumping power, that might actually emerge, at least on paper, as the winner, but it might then violate some of your, not stated here, but some of your kind of more advanced design rules about maximum velocity,
Mm.
maximum pressure.
Yeah,
Yeah, interesting. Okay, well, we'll find out what they do.
that's right. I mean, because another idea is they say, hey, we can just propose wiping out the entire the cooling tower that's there and replace it with an air cooling tower.
Hmm.
Um, I think there's, yeah, a lot of creativity that's possible.
Yeah,
Or
yeah,
propose taking all of the land area of Depot Park. Maybe that's cheaper than having an advanced heat exchanger that's compact. Who knows?
interesting. Yeah, there's an interesting aside here, which I think I mentioned to you at some point in an email, which is well, and you mentioned it too. The this particular power station, the R. Kelly Power Station in downtown, is undergoing a retrofit. So they
Mhm.
did the retrofit to swap out their old turbines with new GE Vernova turbines. But my understanding, at least, I don't know if this is public knowledge, but they actually are also doing a condenser redesign, and I think that's because they did the whole retrofit and they actually tried to like pressurize the system again, and they found that the condenser was damaged.
Oh,
So yeah, so my original plan was to go and see that power station, which is of course closer to UF and the the focus of this particular design problem. But when I started talking with the GRU guys, they're like, "Yeah, no, we're not doing tours because that power plant is still down undergoing a condenser rebuild." So it's okay. We're going to go see Deerhaven,
yeah.
which is much larger, more kind of out in it's halfway between Gainesville and Alachua. It's up on 441. So all the systems are all the same. It's just much larger scale. But I think
Hmm.
super interesting and super relevant that the the students are actually designing the thing that GRU discovered had failed when they did the turbine swap. And so
Yeah,
GRU, I think, had to do their own redesign. So the GRU engineers are literally solving this exact same problem in real time right now as we are.
yeah. I think it's awesome. So maybe when you do the tour, people can drop their ideas.
Yeah, right. I mean, GRU might be hiring and they might
Right,
need
that's right.
somebody to do the condenser design.
Hmm.
So, um, okay. Well, are there any more questions? We're now approaching 2:30. We're at 2:25. So a few more minutes, but any other questions for Lauren while we've got her here?
If we're using air as our cooling fluid, that doesn't have to be like closed loop, right? Like that can just be like ambient air temperature.
Correct.
Okay, cool.
It's actually another interesting thing, which isn't, I don't think gonna affect this problem, but it definitely affects upstream. Which is you, I think you were very, very generous with your ambient conditions. I think, what did you say, like 85 Fahrenheit and
Yeah, I gave
75%?
summer.
Yeah, well, but that's like 75% relative humidity. That's like a nice summer day, right? Like it's in Gainesville, it's
True.
usually in the peak of summer, it's higher than that.
Yeah,
So I've actually noticed, like the university struggles to keep up. And to be fair, the university is not GRU, right? We've got our own separate, cooling and power systems. But there are those water towers like literally hidden all over campus. And once you know what they look like, you kind of can't unsee you once you know what they look like, you cannot unsee them. There's actually one. I'm in MAEC, and if you
yeah,
look out like behind MAEC, there's actually a cooling tower right behind the engineering college, that's hidden
okay,
in a big like brick building. But those things are like going full bore on the days where it's like really, really humid, like 95% humidity,
mhm,
because they like that there's no more capacity in the air to evaporate any more water to, right? So those things have to
yeah,
go like, crazy full bore to get any sort of evaporative cooling to get the water cooled down enough to close the cycle. So I don't think that impacts this problem, right? Because you've given them, um, I think that's right. You've given them the inlet conditions, right? Or you've said,
right.
yeah. So the relative humidity, yeah, shouldn't matter, right? Because all we care about from this point is the temp, because the air and the water are never actually going to commingle, at least not for the condenser that the students are designing. But
Correct. So if we
but
were doing a cooling tower design, then that would matter.
yeah, then
But
that would be
since
a big,
we're, yeah, yeah. So if you see like, I guess if you see a closed loop air cooler, it's called a fin fan cooler versus a cooling tower, which is typically open where the humidity does matter.
yeah.
Um, so yes, that's also something that we have to consider a lot when it comes to site applications in our cooling tower designs.
Yeah, particularly humid environments, because
Right.
you run out of capacity to evaporate any more water into the air and
Mm-hmm.
get the cooling. I was interested, so I'm still kind of fixated on this 7 Rankine, this temperature that you've got on the slide here. And sorry to put you on the spot with all this thermo stuff. I think I've told you this. My dream job is to operate a power plant. Did I tell you that?
No.
Like that's so GRU actually had an opening. I was telling students this a few minutes ago, or a few hours ago, in Capstone today. They actually had an opening for like the chief, like senior engineer, but basically chief power plant operator for the Deerhaven Power Station about a year ago.
Mm,
There was a job opening, and I have not, I've happily been at UF for 7+ years now. And that was the very first job that I considered applying to in the past. I'm like, that's a job where you get to run a power plant all day. That's awesome. That's my dream job. I ended up sadly not applying because one of the requirements is that you needed a PE, professional engineering license,
mm,
which I do have, my EIT in Massachusetts. I took and passed the exam long ago, but I've never gotten the professional license. And that was one of the requirements. You either had it or you had the ability to get it within 6 months, which I don't. Um, so I did not apply for the job, but like I could talk to you about power plants all day. It's like my dream. So I'm interested in this 7 Rankine, that's coming in from the cooling tower. Um, that temperature, although you fixed it here, that temperature
yeah,
is actually dependent upon the relative humidity, right? Like,
absolutely.
in the
That will
real
be,
world, yeah.
hmm right. So that will, in reality, it will vary depending on the ambient conditions, yeah, that it'll be continuously changing. This is, for simplicity's sake, we're fixing the temperature.
Yeah, I got you. Gosh, we should have you come back for a thermo class and have the students walk through the design of the cooling tower for thermo.
If they have fun with this, maybe I'll go bug Dr. Sheffy and we'll do it again.
Yeah, I'm sure he'd be thrilled to have you back.
Yeah.
So, Okay, well, folks,
All
we got
right.
about 1 minute. So if anyone has any final questions, this is the last moment. Otherwise, we'll wrap up. No? Okay,
All
all
right.
right.
And if not, as questions arise, Friday we will have office hours, at least briefly. And we'll make
Yeah,
it longer if people actually show up. So,
yeah, Friday morning, 9 a.m. And Chadi Rashid is going to run that because I'll be launching rockets, assuming it doesn't, rain
yep.
um, that day. So cool. All right. Well,
Awesome.
Lauren, we want to thank you for spending time with us, and we appreciate both you spending the time to give your presentation and coming up with this problem, which is, I think, like perfectly balanced. Like I said, it's you can use effectiveness MTU, you can use LMTD. You've left it just open enough that the students can exercise some creativity, but I think not so difficult that they're not going to be able to tackle it in a week. So I really, really appreciate the thought you put into all that. And um, it's always just, I mean, this is the best part of my job, right? You were one of the just absolutely exceptional superstar students when you were here, and to see you have launched into a successful career and now doing all this work in the real world that's why I wake up every morning and come into UF is to be able to see just incredible professional success like you've achieved. So we really appreciate you coming back and giving back to the students and working with us on this project.
Thank you. I'm very excited. And I know people are going to have very great ideas. So I'm ready for my socks to be blown off.
Very good. Okay, well, we'll
All right.
wrap it up there. So let me unrecord. I can figure out how to do that.